tell him secrets, and then he will literally just be like, he'll tell everybody in front of everyone. I'm like, little book. I told you this.
Okay. All right, well, welcome. Any questions from last time? No questions? Okay.
Maybe a little bit of like the plot, going over the plots a little bit, that seemed a little fuzzy.
Like the steps to do a Bodhi plot? Or?
I don't know. Maybe not. I can look it over.
Okay. So discussion is due by tonight. Homework is due by tonight. So you have different homework, if you've noticed. So you have to download the sheet and write on it and then upload that. So it is going to be different. I don't know if it's going to be good or bad, but it was easier for me. So hopefully, has anybody done the homework yet? Yeah, so quite a few. Was it comments? Like easier?
Took a lot of work once we figured it out, but it's good.
Okay.
Took a bit, but once you got past that, it was fairly smooth.
Okay. So maybe a little bit more time than you've spent in the past, or?
Oh yeah.
Yeah, definitely on a few.
Probably like I spent like maybe 4 times more than I would in usual homework.
Huh. Okay. So more time, easier on me, harder on you guys. Sorry.
Well, I think it's just a harder subject. It felt less confident.
Okay. So also the subject.
Wasn't permanently harder. It wasn't prepared to answer the question.
Okay.
I had to do a lot of research.
Okay.
Homework's quite a bit longer sometimes. We get like
Yeah.
a number of questions, so.
Yeah. It was already prepared, so that's why it was like I usually slim it down a little bit for you guys with the other ones, so that it's just hitting a targeted concept. So if you don't get it the first attempt, then you do more. So that was kind of how it was in the past. So, okay, so it may take you a little bit more time. So if you haven't started it, just make sure you get going on it.
Will our homeworks in the future be like this?
They most likely will for the rest of them. Just because, yeah, my time is even getting more crunched. So we'll see. I've asked the TA support to see if they can come up with some of them beforehand, and if they can in time, then maybe we will go back to that, but we'll see. So you guys can push Luca and be like, please get those done early. And then the other TA, you're welcome to reach out to him also, and encourage them to get those done quicker if you can. If there are, then I can use those to post as instead. There will probably be a few, and like this next exam is going to be another example where for the Bodhi plots, it's hard to do like a quiz format for it. So like with those, you may still have to like draw out the Bodhi plot and then upload that file, or upload that as a file. So get used to drawing those Bodhi plots by hand. So that comes to quiz on Friday will be a Bodhi plot question. So you will need to draw that by hand. So make sure you're very comfortable with that. And so doing the homework, if you've overcome some of those issues and been able to do the homework, you should be able to do well on the quiz. Okay. Any questions on that? Yes.
Are there video resources online for drawing Bodhi plots on the Canvas or no?
Yes. So I did update all of those. It goes. This is not a course. Okay, so yes, and on the iPad it doesn't look like it formats it very easily, but on your desktop it has the tabs, so you can do each one. So I put information on more background on the decibel if you wanted to go back on the background. Semi-like paper is there, so you can print out the paper itself and then be able to draw on that, which is a little bit easier. And then in the Bodhi plot section, I have like an introduction section, which goes through more of the basics of the Bodhi plot. And then there's all of the derivation of the circuit, going from a derivation of a circuit to using the Excel if you wanted to doing it by hand. And then it moved into the approximation method, and then I do have several examples of doing it by hand with real constants, poles and zeros at the origin, and then real and zero poles themselves, and then lots of other examples. So hopefully there's enough examples on there, and then there's some written forms too of examples. So try to provide a lot of support so on that. So definitely have extra things on there for the Bodhi plots. And then for this week, I also I did get material on there. So it also has more about the filters and the LC circuits on that one. And then I am subbing in the other section, and they had some questions about the vector and complex math. So I did put some links today also on the complex math and vectors. So if you want to go back and review on that too. So all that information should be there. All right, any other questions, comments? Okay. All right, so our goals today is to look at the graphs and be able to identify, you started this last time, but also identify the filter type. So low pass, high pass, band reject. Understanding the terminology now from the Bodhi plot. One is resonant frequency, and what does that mean? And then the Q factor, which is the quality factor. And then being able to calculate the resonant frequency. Okay, any questions about what we're going to do today? Okay. All right, so on this low pass, high pass, and band reject, so these should look like we saw last time. One thing to note here, what is the units on the x-axis? Omega, which is in, I heard somebody say it a little louder.
Hertz.
Not hertz, what's the other one?
Radians per second.
Thank you. I heard somebody whispering the radians per second. So remember from the equation, the default unit is radians per second. On this side, this is in volts per volt. And this 1 over the square root of 2, is it next door? Wow, that is very loud. 1 over the square root of 2 is 0.707. Anybody know what that means in dB? No? Minus 3 dB. So this minus 3 dB comes in on the Bodhi plot right at your corner frequency. Remember, it's 3 dB less. This is what this means, is that number, when we look at like the power in a circuit, you look at like average power in a circuit. For DC, it's really easy. You just take a DC value and you use that. Very easy if you have a lot of like variety. It's usually in a DC, you have a small range and it will come, a center point will be shifted up to that value. AC, when you take the average of a cosine or a sine, what is that? It's what?
0.
Correct, it's 0. So that doesn't make any sense for us. It doesn't give us any information to say there's 0 AC power in a circuit. So instead, this term called the root mean square which is where this 1 over the square root of 2 came from. And what that does is it gives us a way to be able to say for AC now, what can be an average, and then we can use that as a comparison to DC. So we use this root mean square, which is the 1 over square root of 2 in volt per volt, which translates to a minus 3 dB. So we use that point as the point where we say, oh, okay, below that point or above that point, that's kind of our threshold point to say, yes, it's passing or not passing. Does that make sense? I lost you guys. Yes, no? Okay. So, for example, keep going on with this one. You can see on this over frequencies, it's not an ideal, once I reach this exact frequency, everything passes. It's not easy to determine that, right? Like, how do I know, like, okay, do I have to wait till I'm here at this frequency and define that as like, okay, once I get that frequency, then everything is passing after that. But that's usually not what we do. We usually say like, oh, well, something close to that. And so what do we mean by close to that? And in terms of electrical engineering, we define that as about 70% of it. So at 70% of what the max would be is where our threshold is, that we say once we've reached that, we consider we're close enough, and now it's considered to be like, yes, it's on or it's off. So that's where we get our 70% is this root mean square. It gives us this. And so at that point is where we say, this is our close enough where we're saying we're kind of on or off for whatever application we have. Does that make more sense? Okay, now I'm seeing some head nods. Okay, so that's what that means. And then for pass band and band reject, remember for these, we want to like focus in on one specific frequency and say like, okay, if it's a band pass, we want to pass just that one frequency. That middle frequency is called omega naught here. This is considered the resonant frequency. For low pass and high pass, that value will be at our corner frequency. So those are the same for low and high pass. And then for band pass and band reject, that's going to be that middle frequency. So that's what resonant frequency is. So now we have different graphs of which kind is this one? Thank you. It is a band pass. And side note, quickly, what is 0 dB in volt per volt?
1.
Thank you. Remember, it's 1 volt per volt. So that's what we're passing. Like, yes, at 1 we are. When it's less than 1, what does that mean?
Attenuated.
It's attenuating, correct. So here you can see that at 0 is where it's passing, and then around that it's attenuated the signal. So here's our resonant frequency. And now you see these interesting, like, oh, okay, some are really sharp, some are wider. So this is called the quality factor, and it is the shape around that omega naught. So when it's really poor, it's going to be wide. So here, it passes all of these frequencies in between that range. So this would be considered a poor selectivity. And so the Q factor is 2, which is low. So quality is for Q. And then you have this one here where you can see it's very narrow. And that one has high selectivity, a Q of 20. So which one do you ideally want for this one? Which one? A low or high Q? Yeah. So this is the one we want, is to have a high Q. All right, what is this one? What kind of filter? Correct, low pass. And for low and high pass, you don't want to have a high Q. Q means resonance, meaning an oscillation in there. That oscillation is what gives you the sharpness. And so for this one, you actually prefer the low Q, meaning no or low resonance to it. So for both these, you prefer this lower, weak resonance to it. And you can see as you have a higher one, there is like a spike up right around that corner frequency. So what is this one? Correct. So this one is a high pass. And, oh, this one has it too, band reject. So forgot to erase that one. So for the band reject, again, you can see the high Q gives you that really sharp corner on it. Okay, so now you can look at these, identify filters, understand what the Q means, the Q factor, and what the resonant frequency is. Any questions about those 3 terms? Yes?
How do you find the Q value without just like looking at it and estimating?
We'll go into that next. Okay. Any other questions? Yes?
With any of these filters, could there be like less curvature but the same basic, like where it'd be more like a square wave for the selectivity, or would that not be?
Yeah. So you can see these sometimes look more like this, which would be kind of a medium to a high, or I mean to a low Q. So low to medium Q on those versus the high Q. So this would not be a great filter for a band reject. But yes, you'll actually see those on some. And then vice versa, the flip side of it, where it looks more like a square. All right, any other questions? Okay, so going into like from a circuit, we could then determine the Q value or, so let's look at that. Oh, one other thing, like at the resonant frequency happens when you have purely real component. So this means that if you have complex components in there, which is capacitors or inductors, that they cancel each other out. And then the result is only pure. So this is one thing that you can use to find the resonant frequency. Okay, so we've looked at a low pass and a high pass last time. If you guys remember, it had an RC only in it. So it only had one time-dependent element in it. So And this was just to remind you, like, these are really, really narrow bands, so we want to have them very precise. One way to create a band pass or a band reject, which was not what we got to last time, is to use two filters. What if I send in my signal, it goes through a low pass, and then I send it through and it does a band pass with a lower frequency start. So then I have this range that goes through and gives me this band pass. So this would work, but it has an issue in that to figure out these exact frequencies of where the high pass and the low pass is, we need to adjust what did the frequency of those depend on. Where did that come from? Thinking about the equation, so we derived it and we had an H of S equation, transfer function equation. And so for the low pass, it reached that point, and what was that value? It came from what in the equation? No idea what I'm asking, right? So the root, right? It was one of the roots. So it's either a pole or it was a 0, and it was the root in the equation. And that was dependent on the R and the C values in the circuit. So let me go back really quickly and show that. So where's my RC? There it is. Yeah, so it was 1 over RC was where you got that value from. So that's going to be common for every RC that you have in there, is that you are going to have, that's going to determine your value. So RC values are not exact. So what we do is called tuning these. And you use a potentiometer for the resistor, or you use a variety of capacitors, and you actually go in there, build it, and go in there and like, oh, okay, now I have it really pretty precise of exactly where I want it to be. But that method of going in and testing it is tuning it. So they need to be each tuned, and that's a lot more complicated. So one way we can not do this is to use, so what we notice here is that each of these has a capacitor in each one of those. So that is a 2-element circuit, right? If you combine them. So capacitor and a capacitor, but what if we have an inductor and a capacitor? Would it be possible to create just one circuit that has both those components in it that would give us the band pass instead? So if I connect a battery to a capacitor, this charges up to whatever value of the battery. So this becomes the same. So if I disconnect it, say really quickly, disconnect it, it has now 10 volts on it, and I hook it up to a inductor, what happens here? So right before that, if I disconnect it from the battery, what happens? What happens to it? It just is going to dissipate, correct? Yeah. So it's going to originally go back to 0. So it charged up, and then I let it sit there, and then it discharges back to 0. So what happens if I connect it now instead of it discharging and just dissipating through its packaging itself, and I hook it up to an inductor? So this is that situation where I just hook it up and I've connected it to the inductor. What's going on? What happens? Any thoughts?
The inductor resists the current that the capacitor is trying to dissipate.
Okay. So it creates current flow though.
Yeah.
Okay, so it creates a current flow because it's moving all these charges to this other element. And yes, the element's going to resist it, but it's going to create now, because there's a change in current, it's going to create this electric field. And so this electric field starts. As more and more movement of the charge and the energy that's in that capacitor moves to the inductor, you get a really big field until nothing is on the capacitor anymore. So now this has the max electric field it can have. And what happens? This can't just, so there's no more movement of energy transferring, right? Because it's all moved off of the capacitor. But now this inductor has everything and it has to stay there. And so it's going to force still the movement of the energy in the bottom still through and keeping that current flow going. So even though there's no more charge on the capacitor, it's all on the inductor still has to move it. So it pushes that current to go onto the plates of the capacitor again. So at first these are very minimal. And that moves me to 3. Oh, oops, I didn't mean to do that one. So that moves me to stage 3. And as that moves, then the current slows down and then the electric field diminishes too on the inductor. So it diminishes the electric field until there's no more electric field on the inductor, or very little, minimal. And all the charge has now moved back to the capacitor. And there's nothing, the inductor is now like basically it sat there for a long time, so it's kind of a wire again. And now the charge is the other way, which causes the current to flow back this direction, which again creates another electric field, and then it's going to move the other way. So you can see in figure 4 and figure 1 here how the charges are opposite. So this is kind of what's happening. And then when I draw this on here, this would be my stage 1, where I'm moving the current. So the current is increasing until I reach all the max, which is when there's no more charge on the capacitor. Then the current stops. And then it slowly starts to move in the other direction. So this is 2, sorry. And then this is 4. And then it goes down, and then we'll come back up, and it creates an oscillation. So just sitting there, they're going to oscillate back and forth and create a sinusoid. So any questions about this? So here's an animation of it, which looks better than my description. So notice current. So current flows one direction, and then current changes and flows the other direction. At the same time, the plates have their charges. So charge on the top, and then it moves to the bottom, and then it moves back to the top. And you can also see the field, the electric field from the inductor changes directions due to the movement of the current and the capacitance charging. Does that make sense? So it's pretty much just moving energy from one element to the other element, but the way it moves it is oscillating it. So give you a second to look at that one. All right, questions about this and how it works? So this is an LC behavior when you have an L and a C together. So if in real life, will this go on forever? No, it's going to diminish out, right? So you're going to see it kind of decay. So you actually need a voltage or a current source in your circuit to kind of keep resupplying it. So by the end of the day, you're going to see like that usually comes from an external source. And then as long as you have that, it can continue to oscillate. All right, so let's now look at a series LC. Okay, so having an L and a C in series and adding on a current source. And I am going to note that we're going to talk about this in all of the time domain. So we know we have current flow through here from the AC current source. So I'm going to describe this by a generic form of cosine with just I peak. And then we want to look at the voltage across the inductor and the voltage across the capacitor. So VL is going to be L di dt. So when I take the derivative, what's the derivative of cosine? Omega t, I should say. Cosine omega t goes to? Thank you. So negative sign, and then you have an omega t, and differentiating it with t would bring out the omega. So you would have minus omega sine omega t. For VC, remember it's C dV C dt is equal to I. So we'll need to integrate both sides of these and to find VC. So VC is 1 over C. And integrate it for IC dt. And so that gives me 1 over CW I peak times sine omega t. So note that this means that VL lags current by 90 degrees. And VC leads the current by 90 degrees. So comparing them, you get 180 degrees difference. So I'm going to come back to this in a second, and you'll see what I'm talking about with leading and lagging. So this is also time domain. So from these equations, here we go, how to find omega naught. So we want to know when there's a resonance between these two elements, and that meant, resonance meant when there was no complex, meaning that they have to equal each other. So go ahead and try to solve. To find omega naught. And so this would mean, like, in addition to each other, they need to equal 0, or one needs to equal the other one. So take a minute to try to find that. And then you can put so what will the value of omega naught be to be able to achieve that? Somebody found an error. So now we have a consensus. So correct. It is 1 over the square root of LC. So just putting these equal to each other. So the sine and the peak will cancel out, and then you have, oh, whoops. So taking the other one over to the other side gives you a minus, so these will become pluses, and then CL omega squared equals 1. So you can divide, and then to get rid of the square root becomes square root of 1 over LC, or 1 over the square root of LC. So now we can look at a circuit and say, oh, this is going to resonate by these values. So this LC is going to determine that location. So I think this answered your question of how do you determine this. So looking at the circuit, if it has an LC combination in it, we can define that resonance as this. All right, so what if we add in a resistor? And instead we put a voltage on it. If we are working at omega naught, what does that mean? It's going to mean that the components L and C have a combined equivalence of 0. Okay, so now looking at this in the frequency domain. So when we solved the circuits before, it was easier to look at this. So if I have a voltage applied here, an AC voltage, R, then these are going to translate to 1 over CS, and this translates to LS. And if we wanted to find the voltage, VC, and say we're just wanting information from the magnitude, this would be the magnitude of VC is going to equal the current and the magnitude of the current equation, which was I of t, I peak, as sine omega t, or cosine omega t, I mean. The magnitude of this is still going to be the amplitude, so it's still going to be I peak. So that will be the current and then times the impedance. So in the case of the capacitor, it's 1 over CS. And now when we're talking about the omega naught is what we kind of want to look at. We're going to change that to J omega so that we can look at the omega naught portion of it. And so here it will be the magnitude of this, which will be 1 over C times J omega naught. And the magnitude of that is what? Oh, sorry, let me go back. So the peak current is actually going to be, sorry, let me get back in. That was from the last problem. So the voltage here, let me write this one, is V source, and that is, and the magnitude of that will be the peak of that one. So the current in here is gonna be what? What's this current gonna be? Thank you. So V source peak, and it will be over R because these two elements cancel out of impedances to 0. So that is correct, that will be your peak. So these are, so sorry, I peak is going to be this. And so this will be V source over R. And what's the magnitude of 1 over Cj omega naught? You guys remember the magnitude of a J component? So thinking of these as vectors, what is the magnitude of AJ? Correct, it's just A. What is the magnitude of A over, or I'll do B over J. B over J. It's just B, right? So what will be the magnitude of 1 over Cj omega naught? What's my A here? Thank you. 1 over C omega naught. And our omega naught, we said, was going to resonate when omega naught was 1 over the square root of LC. So plugging that in, 1 over C, and then at omega naught is 1 over the square root of LC. How can I combine the square root of C over C?
It is C to the negative 1/2. And the numerator is
Multiply the square root of LC over LC.
Uh-huh.
Square root of LC.
I could square that and then just cancel them out. So it'd be C to the minus 1/2, which would be on the bottom. So it'll look like that. So what we notice from this is that this is actually considering amplifying the input source. And I'm going to leave it as an exercise for you guys to find the magnitude of VL to be the same. And then a homework is to do the same process to find that there's current amplification for a parallel configuration. So this shows that the voltage gets amplified. All right, questions on the steps that we did here? Okay. So going back just briefly to the frequency domain and thinking about j omega L and 1 over j omega C. If I was to draw this vector, what does it look like? Thank you. So it has a lineup. And if I was to describe this in terms of magnitude and phase, it is what? The magnitude is?
You will make it.
Omega L. So this value here is omega L, where you can write it next to the vector itself, and then it's 90 degrees that it's shifted. What about 1 over j omega C? What does that vector look like? Correct, so it just points down. What's the magnitude of that one? Correct, 1 over omega C. And then it has the 90 degrees shift. So those plus and minus 90s go back to the leading and lagging. So an inductor generally will always lag the current by that 90 degrees, and the current and the capacitor will always lead the current by 90 degrees. And that's because of the component itself, where it's the vector up and down. All right, so now let's look at an actual circuit. So we were wanting to see what does this produce if we have a capacitor and an inductor in a circuit. But first we had to look at what does the capacitor and the inductor do together. So go ahead and write the transfer function. And you can leave it in terms of LC and resistors. But try and determine what that is. So how do I write this equation? What is my first step? What do I need to do with the capacitor and the inductor to find H of S?
Omega from LC.
So we have to change them into the frequency domain. So that's what you're saying. So j omega L and 1 over j omega C. And you can just use j omega as S if you want to write the transfer function H of S. So the transfer function again is output over input. So you want to write an equation for V out in terms of the components that, and S is usually easier to kind of work with mathematically. So take a second to write that.
And then C equals CS, which is so then solve for C.
I've gotten enough of it. It just becomes fancy for all these Z's. You're running into this shit.
That's Yeah. So the resistor stays? Yeah. That makes sense. But then what I'm saying is. Yeah. Just so but then add something. But now it's
V out is equal to this, which is just equal to another equation, and then we just divide those are each relationship.
But then 1 over C says 1 over 125.
Figure that shit out later. I'm just doing the equation.
That's what I was asking.
I'm like later on in like when you
On the graph with the semi-long, we have.
and then like
Well, you gotta transfer two.
So between those 2 points, it will be
So then it's gonna flip that. And 1 over C, yeah.
It is just a different one.
Don't worry about I still have answers about it.
Yeah, so it's.
But that's how I understand. I need to have. My brain doesn't
No one got, oh, it stopped. Did anybody? Okay, we got somebody got one. Okay. And that, our equivalent, yep, that looks correct. So, so LS and then 1 over CS. And then I'm going to combine these two as one and call them an R equivalent. So these would be R equivalent is just R in parallel with R load. So V out is going to equal V in times R equivalent over R equivalent plus, so I should say the other one was close, but it just needed an R equivalent in there, 1 over CS. But this isn't really our standard form, right? So what do we need to do to get it into standard form? What's our standard form? Top is in standard form. What does this need to do to get into standard form? Go ahead.
You gotta get acid of the denominator of the denominator, so multiply the top and bottom by CS.
Correct. So if I multiply the top and the bottom by CS, that gives me V out. And if I divide by V in to give me the expression of the transfer function, I get R equivalent CS on the top, and then R equivalent CS plus LCS squared plus 1. So this is where you see like, oh, okay, with a squared, I'm going to have a polynomial. And if you guys remember, how do you solve a second order differential equation? Because each of those s's is significant of a differentiation, right? So to solve that, you have to see the characteristic equation of it. And it gets to be a little bit more complicated depending on that characteristic root. So we're going to get into that when we come back to this next unit. But for now, all we need to do is graph this on a Bodhi plot and look at it and say like, oh, what kind of filter is this? So I'm going to use MATLAB, much easier. Okay, so here's my MATLAB code. Oh, it dragged it. Okay, I forgot I wrote this here, so let me just move it really quick. Okay, so here you can see my H equation. It's just basically exactly the same, and then I just use different values of R. So R itself, I did 1 at 60, and then I did 1 at 4. And then we're going to plot this. Is it not letting me? Okay. Okay, so this is that code that was in there. It's taking it a minute to plot these. And as I said before, remember that Bodhi plots have both magnitude and phase. So when this plots the Bodhi plot, you actually get a magnitude and phase change. So what is this one? What filter type? Yes.
No, this is not. Shit, I forgot the name. My bad.
That's okay. Anyone else?
Bandpass.
Thank you. It is a bandpass. So yep, bandpass, it goes up to 0 right at the peak, and then I can just use MATLAB, which is nice. Whoa, if I can click on the right one. You can click on the peak, and it gives you 1.29 e to the minus, or e to the 4th. And what in units, remember, is radians per second. So from this, we get that omega naught is 1.29 e to the 4th radians per second. And then you can see the differences in the Q factor. So which one is the one you would want? And that was H2. So that one was with, and then I'd have to go back and look at the code. And on my code, H2 was an RL of 4. Had an RL of 4. So a lower load gives me a higher Q. So now if I was like, well, I don't want a graphic, can I just look at this? And you could find F naught by 1 over the square root of LC times 2 pi. And it is going to give you the same. So this is, what was it, 1.29. So it's approximately, I'll say, because it's not exactly, 1.29 e to the 4th radians per second. So you can calculate this for different loads and determine which one you wanted. All right, questions about this? Okay. All right, so the last thing we're going to go through is this circuit. So this circuit is, so I'm going to erase this for a second. So you may be wondering, like, what is going on with this circuit? So ideally, like, nothing would be here, but you get a tiny bit of noise on the output of this op amp, and it's going to create a change in voltage, either positive or negative. And so say at first it's positive. This is going to feed back and give a difference in the current. So there's going to be current that flows through the resistor. And if I have a positive value here, there's going to be a slight positive value here. And because this is not connected in the negative feedback, this acts as a comparator. So with negative feedback, we were able to derive the equations for gain of the circuits. In positive feedback, it's going to hit one of those rails immediately. So if I have a little bit of a positive on the positive side, it's going to go to a rail like a comparator. So it is going to go up to the positive value rail, whatever that is. And it's going to create charge onto this LC circuit. And so then that's going to go through the oscillations. And as it goes to the negative, it's going to actually rail it the other way. So then you're going to get the negative rail out of here. And then it will flip again and keep going back and forth. So this is one way to create the function generator or the signal generator in a function generator. So oscillations. So on V2, you're going to get a square wave where it's going to go up and down, and it's going to be at the rails. And then V1, because of the LC having to charge up and discharge, and then they keep oscillating, this keeps enough voltage on it that it will keep it constant. So this will go on forever. And so this gives you a sinusoid at V1. So this is a way to create a sinusoid function. Or it's a circuit that creates that. All right, questions? No? Any questions? Okay. That is all I have for today. So I will see you guys on Tuesday.